Z-scores are distributed with a mean of 1,500 and a standard deviation of 300, you are interested in estimating the average SAT score of first-year students at your college. If you would like to limit the margin of error of your 95% confidence interval to 25 points, how many students should you sample? So let's focus in on this last part, which asks us how many students we should sample. This is telling us to estimate the necessary sample size in order to reach our goals of the limit of the margin of error and the confidence level. So on our hypothesis testing and confidence interval formula sheet, down at the bottom, we see the section, oops, wrong page. Let's see. We see the section, oh, if I can get it, I'm pushing the wrong button here. There we go. We see down at the bottom here, the sample size determination formulas. One for if you're doing it for a mean and one if you're doing it for a proportion. So which one of these do we need for this problem? Well, this said you are interested in estimating the average of something. So that means that you are looking for this formula right here. Okay, now that we have the formula, now these are both equivalent forms. I usually use the second one here. To me, it's simpler because you can just square everything at the end instead of having to square each individual value. So we're going to do this part of it right here. We're going to get the critical value, multiply it times the standard deviation, and divide it by the margin of error. Then we'll take all of that and raise it to the power of 2. So now we just need to extract the information to go into this. So we'll need sigma, the population standard deviation, the margin of error E, and the critical value, which is a Z-score. Okay, now sigma should be given in the problem somewhere. So here I see standard deviation of 300. And then where it talks about the margin of error, it says if you would like to limit the margin of error, and then interjects of your 95% confidence interval, and then gets back to the point to 25 points. So if you read it again, limit the margin of error to 25 points, that is your E. And now we just need the critical value. Now, in order to find that critical value for a two-tailed confidence interval, we're going to need to use the confidence level, and then we'll get the alpha, the significance level, by doing 1 minus the confidence level, and then we'll divide that in half so that we can find our critical value. Okay, so what does this look like on a sketch? This is your standard normal distribution with z-scores across the horizontal axis. And if it's two-tailed, you have a critical value on the left and on the right that'll be twins, where one's negative and one's positive. And each of the tails have half of the significance level, half of alpha, right? So we're going to use the area, we'll get this one by doing norm dot inverse on alpha half, the mean of 0 and a standard deviation of 1. And then we'll make it positive by, I like to use the absolute value function around the norm dot inverse, right? So our confidence level is given in the problem as 95%. Okay, so I'm going to put that as 0.95. Alpha is 1 minus 0.95. And half of it, when you split it up, will give me the left tail area. And then I'm going to do absolute value of norm dot inverse on my alpha half with a mean of 0 and a standard deviation of 1. Okay, so now we have all the parts for our formula. Okay, so n equals let's make a set of parentheses raised to the power of 2. And then we'll go inside of that set of parentheses and we'll do the critical value z-score times the standard deviation sigma divided by the margin of error E. And then we always round up because we want to make sure we get enough sample values. So we round up to the nearest integer, even if normally, like mathematically, normally you would have rounded this to 553. But 554 is how many we need at the least, because the very least we need is 553.1701. And since we can't sample 553.1701 people, we're just going to have to go one up, make sure we get enough. So 554, and we're set.